This is week 3, video 1, and in this section we're going to talk about some topology. Actually, at the very end, the last two videos are going to talk about topological concepts, and then the most of our time this week is going to be spent on conservative vector fields. For the topology, I would just like to point out that on Moodle there should be a topology handout, so make sure to look through that as well as section 6.3 in the text. Both of them are pertinent for this week. Okay. To begin, though, I want to kind of do a sort of a review problem. So we have a vector field and a path, x, going from 1, 0 to 0, 1 in a straight path. So if I were to plot that out, it would be a line that connects these 2 points and progressing in that direction. And then we also have a path y, going a slightly different route. So still going from those 2 points, but it's going counterclockwise around the unit circle. So doing my best to draw a quarter circle here, something like that, and we're progressing like that in red, and so that's y. And we want to compute the vector line integrals for each along the given path. Okay. Well, last week we talked about how to compute these, and we just remembered that for this formula we have to do the composition of these things, and so maybe the parameterization for x of t that we might use would be, let me write this down, this would be maybe 1 minus t comma t, okay, and then for y, unsurprisingly, we're going to use the parameterization cosine t sine t. Cosine t comma sine t. Okay, and certainly I need to mention the restriction. So t is in 0, 1, and close parentheses, and then here t is going to be within 0 to pi by 2. Alright, and so you can go ahead and progress through this. I'm going to tell you, hey, you did it last week, so you can do it this week. Pause the video, do the calculations, and then resume to check your answers. Okay, well, if you did this, then you should have gotten, let's see, I got negative 1/2 for the vector line integral along x under the field, and then for y, I ended up getting negative pi over 4. Okay, so last week, we remember this little tidbit about, okay, well, if you have vector line integrals over a path with the same starting and end point, they should be the same, right? So we are maybe just a little surprised. So let me change this just a little bit. What if, instead of this vector field, we were to do the vector field, let's cross this out and just do y comma x, okay, and consider that vector field. Okay, well, I want you to pause the video and redo the calculations for the vector line integrals and see what we get. Okay, well, if we pause the video and did all this, I believe under this vector field we should have gotten 0 and 0. So in this case, we remember that reparameterization theorem where, yeah, if you parameterize along a different path, they should be equal, but there was an important assumption in there that we kind of left off, that we didn't expound upon last time. And we're going to talk about that next. I'll just mention one more thing before we move on, is that in these integrals, if you were doing them by hand, you probably encountered something like sine squared of t dt, and then integral of cosine squared of t dt. So those are a little challenging to do by hand. Maybe you had to use integration by parts, but otherwise just know that some of these are a little nasty to compute by hand, so if you want to check your answer by Wolfram Alpha, feel free to. Otherwise, know that on a test we would give you those formula. Okay, so yeah, there was some confusion at the end, at the beginning, and why they weren't equal, and so that the discrepancy comes in knowing that we have to have the word that we used last time was a conservative vector field, and so really what we're talking about there is a vector field having this property of path independence. Okay, so if we have a vector field, we call it path independent if the vector line integrals along two distinct paths are equal, and I'll also mention that those two paths must be simple. We talked about that last time, so non-intersecting or non-self-intersecting, and then we have to have piecewise continuous, oriented, so indicating a direction of movement, and so then that's what we would call that's what we would say when two paths are path independent. So for example, we might have a path here. This green thing could be path C. Okay, so that's path C. And then we have another path. I don't know, maybe it's doing this wonky thing. Not self-intersecting though. And I do need that orientation in there, so I'm going to go back and add that into C. And so these two paths we would say are path independent. Okay, and so this path independent property is going to be very important for us moving forward, and when we talk about conservative vector fields, which is where we're going to pick up next time, and also this idea of the fundamental theorem of line integrals, which will be a little bit underwhelming. We'll look at that in the next video.